So good morning, everyone. And let's see, anyone have any questions on stuff? You may have noticed homework 5 has been graded and is out on Gradescope, even though I didn't make an official announcement about it. But you can go review homework 5, request regrades as necessary. I'll give you 3 days to do that. And I posted a key in the weekly module that corresponded to that homework, so you can go, check your work against the key and so forth. All right, then, without further ado, we're in the home stretch, folks, but we also got probably the hardest materials coming up right now. So I'm gonna pick up where we left off last time, which was with a rather difficult example. So these problems that I'm going to be doing today and tomorrow are probably like some of the hardest problems that you're going to see in this class. They're some of the hardest problems that are going to appear on the final exam, right? So like I was writing the final exam and it has some problems like this example. So this example was one that I started on Wednesday, but I didn't have time to finish. Let me just at least show you what progress we made on it. And I'm going to review this, but basically we factored this expression and started setting the terms to 0. And what we mainly did was this sub-example where I solved for where does cosine equal -1/2. Okay, and we found, what was our solution? This was our solution. So I particularly wanted to review this part, or at least mention it, because I'm about to use this in my solution to the problem. So, okay, just save that right there. We already did that work, and we're going to use that work. So, on to today. This is the example from last time. Was we wanted to find where does 2 cosine squared of t plus cos t equals 0. So we're going to solve for the zeros of this function. This is just the continuation of that previous example. And the thing you had to notice was that this expression is like a polynomial in cosine. So what I mean is, me? You got a question? No? All right. So here's what I mean. Suppose g of x is the function 2x squared plus x. So g is a polynomial. Then the function that we're interested in, it's what I would get if I plugged cosine of t into g. That's what I mean when I say this is like a polynomial in cosine. It's a sum of powers of cosine. So in order to solve for where it is equal to 0, the first step is to do the same thing that we would do if we were solving a polynomial equation. And here's something that came up in office hours, actually. So maybe I should make a point of it. How do you solve polynomial equations? You factor them. You set one side to 0, get a 0 on one side of the equation, factor the other side, and set each of the factors to 0. So that's exactly what I'm going to do in this case as well. So for example, if we were factoring 2x squared plus x, we could pull out an x. And then to find the zeros of that, we would set each of those to 0. So that's what I'm going to do now here with this polynomial in cosine. Okay, so let's factor 2 cos squared plus cosine. And we're going to do it the same way I just did with the polynomial in x, which is to say we pull out a cosine of both from both terms. 2 cos squared t plus cos t. If I pull out a cosine, I'm left with 2 cos t plus 1. And now I factored it. So now I can just set each of the factors to 0. Okay, so any questions on that, like first step in the method? You factor it and set each of the factors to 0 like you would do with a polynomial. Okay, so setting the first factor to 0 means that cosine is 0. And so we either get cosine is 0 or 2 cos t plus 1 is 0. Okay, so we've got these two equations to solve. But I've actually done these before. So cosine of t equals 0 was solved last Monday in section 6.1. Let me briefly show you that slide. So let's see, we go back to week 7, 6.1. Where was it? I was graphing cosine. Oh, right there. So that's the graph of cosine, and I wrote down what the zeros are. So the compact way to write them is pi over 2 plus k times pi. Okay, so I'm not going to redo that whole derivation because we already did it. So that's part of my solution. Pi over 2 plus k pi is where cosine is 0. So I can write that as pi over 2 plus k pi for k and z. And recall what z was. Z is the symbol that we use for the set of integers. i.e. it's 0, 1, 2, so forth, and also negatives? Okay, so we've got like half of our solution, the pi over 2 plus k pi, but we also had another factor, 2 cos t plus 1. So 2 cos t plus 1 equals 0 when 2 cos t is negative 1, i.e. cosine t is negative 1/2, and this is what we solved at the end of lecture last time. So let me, well, I pointed that out at the beginning of the lecture. So this has solutions. It was plus or minus 2 pi over 3 plus 2 pi k. For k and z. Okay. Well, then we're done. We found all the solutions. Okay, so I'll just write them all together. There's the solutions for one of the factors. There's the solution for the other factor. So thus, the complete solution set is, let's see, it's pi over 2 plus k pi, and also plus or minus 2 pi over 3 plus 2 pi k. For k and z. Okay, any questions? Okay, so we're about 13 minutes into the lecture. I think maybe it's about time I started asking you some questions. You know, get the old wheels turning, start to wake up. I know it's Monday, it's early in the morning. So here's my question for you now. You can private message me. What are the solutions that are in a single rotation, that is between 0 and 2 pi? Between 0 and 2 pi. So private message me the solutions to the above problem that are in 0 to 2 pi. Because I wrote down all the solutions on the entire real line. There was an infinite number of them. Just tell me the ones that are in 0 to 2 pi. This should be easier than what we just did. And Myrna has a question about, why the heck are we sometimes adding k times pi, but sometimes adding k times 2 pi? So I'll discuss that today. That's a good question. It might help. In fact, I think it really helps to draw a picture. So remember, we were looking for where cosine was, what was it, 0 and -1/2? And if you draw a graph of cosine, I know it starts at 1 when t is 0. So we were looking, let's see, the zeros are as such, and the -1/2, let's see, if this is about -1/2, we get zeros right there, and sorry, my pen's kind of messing up. Okay, if I drew a horizontal line at, man, why is my pen messing up? This is aggravating. It's like not registering. So if I try to draw a horizontal line at -1/2, I can see that it intersects the graph in 2 places between 0 and 2 pi. So it looks like we should expect to get 4 solutions in the interval from 0 to 2 pi. So your answer, it should have 4 answers. And let's see about how many people have answered. Okay, so let's see, if I looked at, well, the solution that we already wrote, for example, I make reference to up here, I can see that, dang, why is this thing not working? Maybe I need to change the battery on my pen. If k is 0 in pi over 2 plus k pi, we get pi over 2. So that corresponds to right there. On the other hand, if maybe I need to change, I'm going to change the battery maybe on my pen, see if that's going to help it. I specifically ordered this stylus from Wacom because I heard they make good styluses. Okay, see if this works. So if k is equal to 1 in the expression pi over 2 plus k pi, we get 3 pi over 2, which, where's that one? That would be right there. There's 3 pi over 2. And uh-oh, now I'm getting a warning that my internet connection is unstable. Geez, I am just Having technical issues all over the place. Let me try the 5G connection. Sorry about that, folks. Hopefully I don't disappear. Okay, so if k is equal to 0 in the expression, well, we had plus or minus 2 pi over 3 plus k pi, then we get plus or minus 2 pi over 3. The plus here would correspond to, let's see, where's 2 pi over 3? That's this point right there. So that's one of them. The minus is not in the interval 0, 2 pi. Okay, minus 2 pi over 3, let's see, where would that be? That would be somewhere like right there, maybe, not in the interval that we want. So let's add a multiple of k to that. Sorry, a multiple of, that's supposed to be 2 pi k right there. Sorry about that. Let's add 2 pi to that. So negative 2 pi over 3 plus 2 pi. What is that? So that is 4 pi over 3. That gives us our third solution, which apparently is right there. Okay, so the 4 answers that are within 0 to 2 pi would be pi over 2, 3 pi over 2, 2 pi over 3, and 4 pi over 3. Now, Myrna was asking, like, where the heck did we get k pi in some of them, but like 2k pi in the other one? Oh yeah, okay, I was just looking at the chat. It's lagging. How's it lagging right now? Can you see me like drawing a face? It's not. Uh-oh. Okay. Yeah. You're right. It's not. Sorry. Okay. Let me reconnect. Maybe I got disconnected or something. My connection was interrupted. Yeah. Sorry about that. Okay. Connected, secured. I have tried this thing where if you like switch Wi-Fi connections so you are temporarily disconnected, you still stay on Zoom. Like I've totally done this before. At least I was kind of surprised that you can actually disconnect, totally lose your internet connection while in a Zoom meeting, and you don't leave the meeting, or at least that's what happened that time. This time, it seems like I did leave the meeting. Am I back? Okay, I'm back. Good. So, ignore that. The last thing that I was trying to write on the screen was just those 4 solutions. These 4 points. Cool. Okay. So now let me address like what Myrna was asking about. Like, why the heck do I sometimes add k times pi, but sometimes 2k times pi, or k times 2 pi rather? So it makes sense to add multiples of 2 pi, because that just gives you a coterminal angle. Like, we would always expect if you can find one solution, then add 2 pi will give you another solution. Let me ask a yes or no question. Pi over 2 plus k times pi is the same as plus or minus pi over 2 plus 2 pi times k. Everyone give me a yes or no on this. And this is for k in z, okay, as usual. For k, an integer. So these are both infinite sets of numbers. Are they the same two sets of numbers? I mean, they definitely share some numbers in common, like pi over 2 is in both of them. 3 pi over 2 looks like it's in both of them. Negative pi over 2 is in both of them. It might help to just like write out both sets. Okay, well, let's start writing them out then. So pi over 2 plus k pi means pi over 2. If we add another multiple of pi, that's 3 pi over 2. Another multiple of pi is 5 pi over 2. Subtract a multiple of pi, we've got negative pi over 2. Subtract another multiple of pi, we've got, negative 3 pi over 2. Now, compare that with this set, which is going to look like, okay, so if I start at positive pi over 2, then I add 2 pi to that, what's that, 5 pi over 2. If I subtract 2 pi from that, that's negative 3 pi over 2. So these ones in purple correspond to positive pi over 2 plus 2 pi k. Now, if I do the negative ones, if k is 0, that's negative pi over 2. If k is 1, what's that, 3 pi over 2? Add 1 to that, you would get, what is 7 pi over 2, and so forth. So it looks like it's all the same points. So the answer should be yes. It's two ways of writing the same set. The reason the answer was yes was because pi over 2 and negative pi over 2 already differ by a multiple of k. Okay, so if you subtract one multiple of, sorry, did I say multiple of k? They already differ by a multiple of pi. So negative pi over 2 plus pi is positive pi over 2. Pi evenly divides 2 pi. So adding, it's kind of a lucky coincidence that these two sets happen to coincide, you can also visualize them by looking at a graph of cosine. So if we look at a graph of cosine, we see here is pi over 2, and we get the other zeros that look like that one by adding multiples of 2 pi. So let's see, did I do that right? There is a distance of 2 pi. There is another distance of 2 pi. And here is negative pi over 2. Wait, did I miss? Oops. Did I miss a 0? Yeah, sorry. There. Yeah, there's negative 3 pi over 2. Sorry. This is negative 5 pi over 2. And here is 3 pi over 2. So again, these all differ by 2 pi. Okay, so yeah, I know it's kind of confusing. Hopefully that helps to explain it a little bit more. So let's do some more practice with this. We're going to do more practice with this today. That finishes this problem, however. Any more questions before I move on to the next problem?
It seems there's still confusion about the previous problem.
Okay, can someone speak up? I can't keep track of the whole chat.
So they just had a question about why one of the answers was, I think, 4 pi over 3. If you started with a negative angle, I think that's where they seem to be.
Okay. Let's see. So if I add, let's see, did I do that right? Negative 2 pi over 3. And if I add 2 pi, that's negative 2 pi over 3 plus 6 pi over 3, which is 4 pi over 3. So that was the coterminal angle with negative 2 pi over 3. These two angles right there are coterminal. Rebecca?
So when you're like trying to find the solutions, are you basically just plugging in 0 and 1 for k? It's like, isn't that what you just did?
That is what I did. Yeah, usually 0 or 1 are sufficient because usually, like, if we're going to find answers, we're obviously going to use kind of like the easiest angles. We don't want to go, start off at like 720 degrees to start finding our solutions. So yeah, usually if we want to come up with angles that are close to 0, those are the reference angles that we're going to use to write our answer. I wouldn't say that that's a rule, however. You don't have to do that. It's just sort of easiest. I definitely recommend drawing a picture, though. I think that what best illustrates where the zeros are is this graph I drew of cosine, where you can see where the solutions that we are interested in are. And like if I wanted to show all of the solutions, then I would start doing, okay, so there's also ones like right here. There's also ones, damn, my pen's messing up again. What the? also ones on the left, and so forth. So yeah, I definitely recommend like draw a cosine graph. You should be very comfortable and used to just quickly sketching a cosine graph. So let's practice that some more with the next problem, which starts off looking ostensibly different. Okay, so the example now is to find the zeros of this function. But we cannot start this problem the same way that we started the last one, because it's not even a polynomial in like a single trig function. It has both cotangents and cosecant squared. So in order to solve this problem, before we can proceed like we did on the last problem, we first have to employ a trig identity. And this partially comes down to a matter of experience. So let me remind you of our three Pythagorean identities. So these should be sort of like second nature, which is that sine squared plus cos squared is equal to 1, 1 plus tan squared, 1 tan secretary, and cottage cheese, 1 plus cotangent squared equals cosecant squared. So just you should always have those in the back of your mind. And in this problem that we have at hand, you will see that we can put everything in terms of just one trig function, because anytime you see a cotangent squared, you can rewrite that in terms of cosecant squared using this identity. And again, this is partially just a matter of experience. Once you've done this enough times, it starts to become second nature. So that's going to be the way that I proceed in this problem, because looking at the expression, once I do that, everything will be in terms of cosecant. Okay, so again, that's how I know, or at least have an idea that this is what I should do. Once I use this identity to get rid of cotangent squared, then everything will be in terms of cosecant in this expression. So use the fact that cotangent squared of theta is cosecant squared of theta minus 1. Then the expression 2 cotangent squared of theta plus cosecant of theta minus cosecant squared of theta is the same as 2. So I'm plugging in for cotangent right here and replacing it with cosecant squared of theta minus 1. I now have an expression that only has cosecants in it. So it's like a polynomial in cosecant, which is now kind of like the previous problem. I can simplify this. Let's see, this is 2 cosecant squared theta minus 2 plus cosecant theta minus cosecant squared theta. And let's cancel one of these cosecants. And I just got cosecant squared theta plus cosecant theta minus 2. Okay, so try to remember what we did here. I started with the expression that was given. I used a trig identity to rewrite it in a totally equivalent expression. So what I started with and what I ended with, they're the same thing. So it suffices to set what I ended with to 0. Okay, so that is how we proceed. So thus, set cosecant squared theta plus cosecant theta minus 2 to 0 and solve. And that's your solution. And we can proceed to solve that now because it's now clearly a polynomial in cosecant of theta. Ebony?
I had a question because I'm confused where you crossed out 2 and cosecant square. Like,
I just combined, yeah, because I had 2 cosecant squareds, and then I subtracted one of them. So I was able to cancel them, or cancel one of them anyway. And
okay.
just right.
Now.
Okay.
Thank you.
Mm-hmm. Yeah. Thank you for asking. I hope everyone don't be shy to speak up. This is, like I said, don't be surprised if you find yourself confused on this lecture and the next one. Like, I'm not going to lie, this is going to be the hardest stuff that we're going to be doing in the whole class. Okay, so it's you might think it's hard. I'm sure everyone is going to think it's hard. Okay, so we have expressed our function as a polynomial, which I can now factor like we did in the previous problem. Okay, so what I just did was I employed an identity to write the original expression as a polynomial in cosecant of theta. So now I can proceed to factor it. Anyone know how this factors? Can someone factor it for me? Rebecca?
I tried doing it. So what I did was, well, I kind of like put it into terms of x so that it would be easier, but I can just.
Oh, I like that. What's it like if you wrote x in terms of x instead?
I wrote x squared plus x minus 2.
Nice. X squared plus x minus 2. That's a great idea. I recommend you do that because it's often like easier to think about how to factor it when it's in terms of x's. So good. That's very good. And then how does that factor?
It factors to x plus 2 times x minus 1.
All right. That's x plus 2 times x minus 1. Very good. So that means that cosecant squared theta plus cosecant theta minus 2 factors as cosecant theta plus 2 and cosecant theta minus 1. Cool. So we factored it. And now, as with the previous problem, we set each of the factors to 0 and then solve that. Okay, so this will give us 2 possibilities. Either cosecant theta plus 2 equals 0, or cosecant theta minus 1 equals 0. So I'll solve both of these like individually. So from the first one, that's the same as cosecant theta equals negative 2, which I think it's easier to do everything in terms of sine and cosine. So let's write that cosecant, let's see, what the heck was that? That's 1 over sine. So this is the same as 1 over sine theta equals -2, i.e. sine theta equals -1/2. So it turns out that sine theta equals -1/2 is what we need to solve. So let's look at the other term. We'll solve that in a second. But the other expression, this one, can also be written in terms of sine. So this is where cosecant of theta equals 1, i.e. 1 over sine theta equals 1, i.e. sine theta equals 1. So it turns out that our solution is where sine is 1 or -1/2. Okay. I think I'm going to do a quick little activity. I want you to tell me how many solutions in 0 to 2 pi are there? Right, to what we just figured out, to sine equals -1/2 or sine equals 1. And you know what? How about you just hold up the number of fingers? Either hold up 1 finger, 2 fingers. I wanna see people holding up fingers, and just keep them up there so I can take a look at everyone and see how many fingers we've got up. So you might want to draw a picture. You might want to draw a graph of sine. Now there's no need to flip someone off. Oh, okay. Let's see. Some people apparently follow the German tradition of holding up like a finger with their thumb. If anyone remembers Inglorious Bastards. Whoa, man, there's a bunch of people whose cameras are off. Can you folks turn your cameras on, please? Okay. Got the Star Trek. Let me try to draw a picture for this. Okay, I suppose you can put your hands down, folks. So the graph of sine, which hopefully starts to become second nature. Looks like this. And the maximum value of sine is 1. The minimum value of sine is -1. Where does it equal? Let's do where sine is equal to 1. Valentina?
Would it be pi over 2 plus 2 pi k?
Ah, okay. So that would be, so the first one is at pi over 2. Yes, right there. And so the next one would be 2 pi after that. And the one before it would be 2 pi before that. If we're only focusing on the interval 0 to 2 pi, which actually might sort of make this a little bit easier, then we only need to worry about the one at pi over 2. So in a second, I will ask you what all of the solutions are. If we're only concerned with the ones in 0 to pi over 2, then we get one right there, and we also we're looking at where sine was -1/2. So if I draw a line at -1/2, that's going to be a horizontal line down here. And if I only looked at the ones that were within 0 to 2 pi, then it looks like we get a solution right there and right there. So I see a total of 3 solutions. And okay, so there are 3. The answer is 3. Let's keep up with the practice. How about, can you private message me the 3 solutions in 0 to 2 pi? And Valentina correctly identified one of them. But there's 2 more that are as yet unidentified. So this is a typical trig problem to figure out what those are. You can see it builds. You got to know how. You got to be able to solve. For when some trig function, when sine is equal to some number, before you can do these later problems. So please, and everyone do this, please. And your answer should conform to what our picture looks like, right? So we're basically asking what these 2 points are, because we already decided that pi over 2 was correct. But what are these other 2 points? And you can see that, well, they appear to be between pi and 2 pi, because let's see, like, there's pi. So what is this and what is this? It's 2 numbers that are between pi and 2 pi. Some people are getting it. whatever it is, if you take the sine of it, it should be -1/2, because those are the intersection of the line -1/2 with the sine graph. Now, it might help to use the unit circle, actually. So maybe let me go grab a copy of that real fast. And where's the unit circle? So if we look at the unit circle for where does sine equal -1/2, sine is the y value. So we're looking for where the y value is -1/2, and we spot it right there. Y is -1/2, and right there, y is -1/2. So these two directions correspond to angles whose sine is -1/2. Now, since we want the version or coterminal description of this angle that's inside 0 to 2 pi, that means that in particular, we want this angle and this angle. So we can just actually read those angles off from the unit circle. Apparently, the first one is at 7 pi over 6. So this is 7 pi over 6. And the second one apparently is at 11 pi over 6. So the answer is pi over 2, 7 pi over 6, and 11 pi over 6. Cool. All right, any questions? So in this problem, we first solved it within 0 to 2 pi, but I could ask you for what the general solution is, right? Instead of just restricting our perspective to 0 to pi, what if I asked what the general solution was? So all of them, all infinite solutions. Now that we've figured out what these solutions in 0 to 2 pi are, it's kind of easy to find all of them. Just add multiples of 2 pi to all the answers we found. It's not like we're going to accidentally double up any of the answers, because once you add a multiple of 2 pi, then you will be outside the interval 0 to 2 pi if the angle you started with was inside of it. All three angles we found were different, so simply just add 2 pi k to the three answers we found, and that will give us all the answers. So the general solution dang it. The general solution is to add 2 pi k to each of our solutions that lie in 0 to 2 pi. So we will get pi over 2 plus 2 pi k, 7 pi over 6 plus 2 pi k, and 11 pi over 6 plus 2 pi k. Cool. Okay. Any questions?
How would you find like the 7 pi over 6 and 11 pi over 6 without the unit circle?
Well, if you looked at the graph of sine, then we roughly like had an idea of where they were. So we know that they're somewhere between 0 and 2 pi. So yeah, like how could you do that totally by hand? You could forget about the sign, the plus or minus for the moment. So ignoring the plus or minus, just forget about that. Where does sine of, let's say like some alpha, let's say, equal to 1/2? I'll take care of the minus in a second. This happens on one of your special right triangles. So you can draw a right triangle for which the opposite side is 1 and the hypotenuse is 2. And if you can do the Pythagorean theorem, or maybe you just recognize it at this point, that the other side of this triangle would be √3. So you need to recognize that this is one of our special right triangles. There's only 2 special right triangles, all right, the 45, 45, 90, or the 30, 60, 90, and this is one of them. So if you recognize that this is actually a 30, 60, 90 triangle, or sometimes also written as 1/2, 1, and √3 halves, then you see that, oh, the angle that we're looking at this triangle from must be 30 degrees. Okay, so you just have to recognize that these ratios are the same ratios that appear in a 30, 60, 90 triangle. So that tells you you're looking at a 30-degree angle. So that tells us that our reference angle is 30 degrees. So now, since sine of 30 degrees is 1/2, to find where sine of, let's just say, x is equal to -1/2, draw some triangles with reference angles of 30 degrees. So the fact that the sign is negative tells us that we're in quadrants 3 or 4. So we're somewhere down here, and our reference angle is 30 degrees. So reference angle with the x-axis is 30. So we could either be 30 degrees below the negative x-axis or 30 degrees below the positive x-axis. That's the only 2 places, that's the only two directions in quadrants 3 or 4 that have 30-degree reference angles with the x-axis. So that tells us the only two directions possible, which is this, which is pi plus pi over 6, or 7 pi over 6, and the other one, which, I mean, you could write it as negative pi over 6 if you want, or you could also write it as negative pi over 6 plus 2 pi, which is the one that we were actually asking for in the problem, at least in order to find the angles that are inside 0 to 2 pi. But yeah, that's a good question. I'm glad you asked. It's kind of tough, isn't it? Does that help clear it up? Okay, cool. Thanks for asking. Any other questions?
Yeah, for the general solutions, can you write 2 pi k minus 1 pi 6? Or would it be wrong also?
Sorry, could you write, say that again?
So you know for one solution is 11 pi over 6 plus 2 pi k, right? So what if you do 2 pi k minus pi over 6?
2 pi k, minus pi. Yeah, good. Yes, yeah. Good point, Carlos. So Carlos noticed that you don't have to use, you can replace this 11 pi over 6 with any other angle that's coterminal with that. Yeah, you don't have to use 11 pi over 6. You could also write negative pi over 6. So yeah, let me write that. So 11 pi over 6 plus 2 pi k is the same as negative pi over 6 plus 2 pi k, because it's just like differing the angle you started with by 2 pi, which means it's the same angle. So these are both the exact same sets, and they are both totally valid ways to write your answer. And in fact, Juan suggests drawing a picture, like if, let's say, here's 0, and here's 2 pi. So here's 11 pi over 6, and here's negative pi over 6, and the distance between negative pi over 6 and 11 pi over 6 is 2 pi. So if we start adding or subtracting multiples of pi, like the next one would be negative pi over 6 minus 2 pi, whatever the heck that is. I guess that's negative 13 pi over 6. That would be another 2 pi away, but notice that that's the same thing as 11 pi over 6 minus 2 times 2 pi. Yeah, so it's like the k equals negative 2 version.
Chatty, you cut out, your audio cut out a little bit.
Professor Ciotti, we can't hear you. We can still hear you.
Can you hear me now? Oh, okay. Weird. Yeah, I wasn't muted. I don't know why it stopped. Okay. So what I was saying was, if we go 2 pi below negative pi over 6, that would put us at negative pi over 6 minus 2 pi, which is negative 13 pi over 6. So negative 13 pi over 6 is negative pi over 6 minus 2 pi, i.e. negative pi over 6 plus 2 pi k, with k equals negative 1. Alternately, though, negative 13 pi over 6 is 11 pi over 6 plus 2 pi k, with k equals negative 2. So it doesn't matter which of the two forms of your answer you use, you end up with the same points. They might correspond to different values of k, but that's fine. What matters is that in totality, it's the same set of points. And yeah, this is maybe some of your first exposure to infinite sets, but that's what calculus is all about. All right, that's how calculus differs from all the math you've done up until that point. Is in calculus, you're starting to think about infinities, the infinitely large and the infinitely small, and weird things start happening once you start making these assumptions and considerations, and it ends up giving you all these crazy powerful tools. So just erase that. Cool. Okay, let's see. So it doesn't look like I'll have time to start on the next section, unfortunately. I was hoping to. Okay, yeah, I'm definitely not going to get to 7.3, which I wanted to at least start today because it's hard. It's got some tough formulas. But let me just mention a section we're skipping, which is 7.2. In the interests of time, we're not going to cover this section, but you should know that it exists. 7.2, it contains some formulas. Specifically, it contains the addition formulas, the difference formulas, the sum to product formulas, and the product to sum formulas. So all these formulas are kind of hard. You can see why maybe we weren't going to include them. And most mathematicians don't even have these formulas memorized. I mean, I have some of them memorized because I've used them so many times, but usually we just look them up. So it's not like you would be expected to memorize them, even if we were covering this section. But notice, like, for example, there's a formula for the sine of the sum of two angles. It's sine alpha cos beta plus sine beta cos alpha. For example, that's actually, I just rewrote this formula. And the reason that I'm even talking about this section right now is because I want you to know that these formulas exist. Okay, so you don't have to know them, but know they exist. So, you know, in theory, you could go look them up and apply them. And what they do is for example, in the sum identities, they give you a formula for the sine of the sum of two angles in terms of the sines and cosines of those angles. Similarly, you could have a formula for the difference, the sine of the difference of two angles. Similarly, they have formulas for cosine of the sum or difference. Some of the formulas down, no, not those. How about these ones include, for example, a formula for sine alpha times cosine of beta. And it's 1/2 sine of alpha plus beta plus sine of alpha minus beta. So again, I just want you to know they exist. And in the next section, which we are going to cover, we're just going to focus on 2 special cases of those formulas. Namely, the double angle formula and the half angle formula, which, yeah, since I'm out of time, I'll have to do that tomorrow. And that is it for today, folks. Any questions? All right, cool. Well, I can hang out and answer any questions any of you may have. And I'll be in office hours in 15 minutes. And everyone else, I'll see you all tomorrow.
Have a good one, Professor Ciotti.
All right, thanks, Jose. You too. Victoria?
Yeah, I have a question. On the final, would it be more kind of towards the questions that are like in mom, or would it be similar to how you do it during class?
The final questions will probably be kind of like the study guide problems, at least like the new ones. So I put out that study guide, well, to help prepare you for the final. And I didn't actually post a set of questions on mom because I thought that studying the ones on the study guide might actually prepare you better, you know? So the new material questions will be similar to those. The questions on old material will be similar to problems from the homework or quizzes or midterms.
Okay, thank you.
Mm-hmm.
Okay, have a nice day, Professor Ciotti, and then I'll finish grading the quiz, and then I'll send you an email.
All right, cool. Thanks, Juan. Let's see. I think I have to reboot my laptop since it's acting weird. So I'm gonna have to shut this down. Juan or Juan Villalobos or Rios, if you want to ask questions, just come to office hours. I'll be there shortly.
Okay. Thank you for today.
All right, sure.
Have a nice day.
All right, you too, Juan.